Let us talk about this problem. We are given two binary arrays of same size. We need to find out length of the longest common subarray. So when I say common subarray, it means the starting and ending indexes of this subarray should be same in both the arrays. So we need to find out such a subarray in both the arrays such that the sum of elements in both these subarrays should be same. Let's understand the problem with these examples. So if you see this array and this array, and if you consider all the subarrays, the common subarrays, you will notice that there are many subarrays which have same sum. For example, this subarray has sum 1 and this subarray also has sum 1, and starting and ending indexes are also same. But this subarray which I have highlighted here, this subarray has the longest length. This subarray has length 4, and the sum here is 1 and the sum here is also 1. Right, 3 zeros and 1 1. Here also 1 1 and 3 zeros. Let's see this example. In this example, the longest subarray is of length 6. Length 6 subarray having the same sum. Right. In this example, there is no subarray with the same sum. Every subarray has a different sum because there we have 3 zeros and here we have 3 ones. Right. So our output is going to be 0. Now let's see this example. In this example, we have two arrays and there is only one subarray with common sum, right? And this subarray is having sum 1 here, sum 1 here. Now please pause this video and try to write down a function that takes two binary arrays and finds length of the longest common subarray with the same sum. Please try writing the solution using a naive method first. Let me give you a hint about the naive method, and you must have guessed it. We are going to traverse through all the subarrays of both the arrays, and for every subarray we are going to compute the sum in the first array and in the second array. And if both the sums are same, then we are going to compare the length of current subarray with the maximum length that we have seen so far. And at the end we are going to return the maximum length. Here is implementation of the naive solution. I have written implementation close to C++ programming language. If you are programming in Java, there are not many differences. You don't need to pass the size of arrays in Java. You can get the size using ARR1.length or ARR2.length. They are of same size. Instead of max, you need to use math.max in Java, right? Rest is same. So what are we doing in this implementation? We first initialize the result as 0, right? Then we run a loop for every element. Basically, we generate all the subarrays, right? J is the ending index, I is the starting index. For every subarray, we compute the sum, right? For every element that we traverse, we keep on adding the sum 1. Array 1 j to sum 1 and array 2 j to sum 2, right? And if they become same, then we compare j minus I plus 1, that's the length of the subarray beginning with I and ending with j, with the result. And if the length is more, we update the result, right? So if you see this example, initially result is 0. When you run for I equal to 0, you are going to consider all subarrays beginning with index 0, and the longest subarray that has 0 index as the starting index is of length 2, right? There is no subarray which is of higher length and has same number of zeros and ones. So we update the result as 2 from 0, right? Now when we come for I equal to 1, when we are at this index, then we find a j equal to 4, and at this index we have the length 4 and sum 1 and sum 2 are same. So we update the result as 4. For I equal to 2, 3, 4, 5, the result would not be updated, would never get more than 4 length, right? So our output is going to be 4. The time complexity of the solution is clearly theta n square, right? And auxiliary space is clearly big O of 1. Now please pause this video and try to write down an efficient solution that works in linear time. Let me give you a hint first before I talk about the efficient solution. The hint is we are going to reduce this problem into the problem of longest sub-array with 0 sum in an array. Please pause this video now after this hint and try to solve this problem with this hint in linear time. Here are the steps of the efficient solution. What we do as a first step, we create an auxiliary array and we store difference of two arrays in this auxiliary array. We can either store array 1i minus array 2i, or we can store array 2i minus array 1i. For example, if you are given these two arrays, the difference array is going to be 0 minus 1 minus 1, 1 minus 0, 0, 1 minus 0, 1, 0 minus 1 minus 1, and so on. Right, so once you build this temporary array, now your problem reduces to find the length of the longest subarray with 0 sum in this array. For example, here you can notice the length of the longest such a subarray is 4, and you can notice in both the arrays we have length 4 common subarray with the same sum. Let's see how does this work. What is the reason behind working of the solution? If you take a closer look at this temp array, you can notice that we are going to have 0 values in this temp array when both array 1 and array 2, they have same values at those indexes. For example, we have 0 here because these two arrays have 0. These two arrays have 0, so we have 0 here. When two arrays would have 1, then also we would have got 0 in the temporary array. And we are going to have a value -1 when this array has 0 and this array has 1, which means this array has an extra 1, right? And we are going to get a value +1 when this array has an extra 1, right? So if you have all the zeros, then your whole subarray is going to have the sum 0. If you have some zeros in your temp array, for example, we have 2 zeros here, then we can add more elements around this subarray, right? If adding those elements keeps the sum as 0, right? For example, we added these 2 elements and we got the sum 0. And this is logically true, right? Why? Because the extra elements are going to give you some 0 only when there is an extra, if there is an extra 1 in first array, then there is an extra 1 in the other array, 1 minus 1 combinations, right? Those things are only going to give you 0. Now let's see the third case when you do not have any 0. For example, here also we had something else and we did not have 0. In those cases, 1 and -1 combinations, they can give you zeros, right? They can give you some subarray 0, and 1 -1 combination means 1 extra in one array and -1 extra in the other array, right? So this 1 -1 combination works perfectly fine, and it might be possible that two arrays do not have any common subarray with 0 sum, right? For example, if you have all the zeros here and all the ones here, like we discussed an example in the example input output, in this case what are we going to get? We are going to get all -1s, right? So we are not going to get any subarray with 0 sum. If you have all 1s here, all 0s here, then you will get all 1s, right? So this solution works for all the cases, logically true, right? We can show it all 0 case, some 0 case, no 0 case. By considering these 3 cases, we can show that it works. Now what is the time complexity of this? See, the first step clearly takes theta n time and theta n auxiliary space. And we have already discussed this problem earlier. The second step, it's going to take big O of n time and big O of n auxiliary space. So we can say this solution takes theta n time and theta n auxiliary space overall. Big O of n plus theta n can be written as theta n or big O of n, right? So we can say theta n time and or theta n auxiliary space.